Hello and welcome to another research discussion, this time a new fundamental discovery that emerged from my continuing investigations into predicting the future. This astounding encounter all begins with sample size, or the number of training samples per predictor in a data set. Sample size error is the most unusual error in the machine learning universe. It is both data and model independent, and yet it is created solely within the model. It does not combine with other forms of error, but it sets the baseline error of the model. Other errors must rise above the level of sample size error to be seen. And as with my previous research, this investigation involves the theory of bias and variance. Now, I know what you're thinking. Dave, what more can be done with bias and variance? It's just prediction error decomposed into two elements, bias for the training data and variance on the testing data. Yes, but there are nuances even to this seemingly simple theory, and sometimes in the nuances we can find fundamental truths of the universe. This is one of those times. The authors of this landmark article took note that all data sets from the infinite multitude, the capital D, would possess different biases across models, some low and some high. A data set could be high bias in one model and low in another. But what if we took training set to mean all possible variations of the same data set? Some variations should be low bias and some should be high, and the all model dependent, but from the same data set. Now, in this way, we can see how homogeneous our data is, and if different seed values in the data partitioning process result in different distributions of model accuracies. So, a synthetic population estimator was constructed. Random forest was chosen as the core model because it is the most generalizable model. Rarely the best, but always in the top tier across most data sets. And the bonus is that it won't deliver an artificially broad population distribution, such as logistic regression or k-nearest neighbors might do. Now, if the data set had less than 10,000 samples, then 200 variations were created. Otherwise, 100 variations were used for expediency, because with large data sets, this can take quite some time to complete. Now, because the Vetnik-Chervonenkis dimensional bounds affect both training and test, covering both modeling and prediction, a 70-30 split was used to ensure adequate generalizability on the test data. And after conducting numerous experiments, it appears that ADASN adds more noise than information when the class imbalance is less than 60-40. So that is our threshold for its application. Now, please remember that what you're seeing in the charts to come are model accuracies as predicted on the test data. All my research results are on test data, and this is no exception. And we want dispersion, that's population dispersion, to be smaller rather than larger because of its association with future risk through model selection failures. This has been confirmed in the follow-on research, Model Selection Done Right. And here are our 25 open source data sets with a broad range of sample sizes and predictor configurations. Some are all floating point, some are all integer, and some are a mix between the two. Now, whether this is a representative sample from the over 31 million data sets in Google's dataset search engine, I don't know, and we may never know, but it is what we have for now. With this data set, there's an 11.6% difference between the extreme low bias model, coincident with lower accuracy on the test data to the far left, and the ultimate high bias model, coincident with higher accuracy on the test data to the far right. And now you can see why this research project began with the search for a better method of model selection. The dispersion range has shrunk considerably with the IBM employee attrition. But in this histogram, one can see that test data results may show gaps. For this sub-project, we are only interested in the low and high bias terminals and the distance between them. Here is another example, this time with our leader in sample size, with over 7,900 samples per predictor and a population dispersion of just 1%. When we take all 25 data sets, extract dispersion values, and perform a nonlinear power law regression between samples per predictor as the x and dispersion as the y, this is what we get. The Spearman correlation demonstrates a very strong negative monotonic relationship between sample size and dispersion. It turns out that sample size explains more than 56% of the variance of population dispersion, the range of future risk in terms of model selection. The p-values are quite small, below the 1% threshold, but as to whether this means anything, I don't know. But they are small, so this is a good thing. And this plot shows that there are two distinct linear paths to follow for decision making, the vertical and the horizontal. This is like the song White Rabbit by Jefferson Airplane. You know, the one where one pill makes you larger and one makes you small? When the sample size is small, the largest difference can be made by adding the smallest number of samples. And when the sample size is large, the smallest difference will be made by adding the largest number of samples. And herein endeth the lesson. Even the book, Learning from Data, published by the authors from Caltech, says that 10 samples is the baseline minimum. So this notion is widespread. But as we have now seen, there is another dimension to sample size beyond the single model. There is a population dimension that should be, in fact, must be considered. How does sample size error even have a population dimension? Should be our first question. The answer to that one may point us in the direction of question number 2. How can it be responsible for 56% of the explained variance of population dispersion? This is an enigma wrapped in a mystery, surrounded by a riddle.